This video has been very troublesome. I'm trying to debounce my switch here, and I've had many false starts, and I've gone down some pathways that just totally failed to work. And normally I don't have a problem showing mistakes on the channel, but I didn't want to have, an entire 20+ minute video of an hour worth of work that ended with utter failure. So I threw my first attempt away, and then my second attempt ran into technical problems and I had to throw that away. So I'm on my third attempt now at doing something which seems like it should be simple, which is debouncing this button. Now, bouncing is a thing that occurs because of the physics of the switch, I think, mostly. That there's springs in here, but also the metal itself is actually flexible. And so when the contacts bump into each other, they shake a little bit. And that shaking causes the electricity to flow while it's shaking, and that means that this counter chip is getting more than one pulse to count. If I had an oscilloscope, I could show this pretty easily, but I don't have an oscilloscope, so you can probably imagine it. The oscilloscope measures voltage like over time. It's just that it measures it at very, very quick time slots, much faster than you can perceive, like nanoseconds. If you were to imagine the voltage going through the switch, it might start at nothing and then spike up when I push it, but then it might drop down and do a bit of this wiggling before it settles down, or up in this case. That causes the chip to read these, to mistakenly think that I pressed the button a bunch of different times. Now, it also turns out there are other sources of bounce that I hadn't even considered, and I found this out after my first failure and I did some more research. There's things like electromagnetic fields, just in the environment, like a lightning strike nearby could cause a pulse, causing an EM wave to hit your wires and create just a little bit of a fluctuation. It could register as just a very brief signal. It can mess circuits up. So the first time I went searching for a solution to this in my first attempt at the video, I ran across something called a single shot circuit, I believe it was called, and it was made with 2 XOR gates. And logically, to me, it sounded logically plausible. A signal would happen on one of the gates, and then it would go through this resistor capacitor circuit, which created kind of a delay. And then it would go into the next XOR gate, or maybe they were NOR gates, but whatever they were. And then it circled back around, and it would keep the circuit alive as long as you had given it a signal that was long enough for that resistor capacitor delay. It was something like that. Again, I don't fully understand it. And I'm not going to show the circuit that I actually did because I don't want to give people the wrong idea, because it did not work. So I couldn't figure out how to debug it, so I gave that video up, and I went back to the drawing board, or I guess the research board, and kept searching. And then I came across this site. Now this site, or page, I guess, was one of the first ones I came across that actually explained the problem cleanly. It didn't get too distracted and bogged down and stuff. And it was like, here's the fix. Now, I had seen a circuit similar to this before, which it looks to me it'd be pretty standard now that I know what to look for. But I had seen it on some other pages when I was doing my initial searching. But I often got the impression, largely because of labels like this, that maybe this was something you only did on Arduinos, and that, it was skipping hardware. Or some pages even led me to think that this was somehow an old way to do things and wasn't how we do things nowadays. And, now we use them with these chips. And I guess there are debouncing chips, but, I don't have one. So I kind of got, somehow very misled on what the right way to go here. And some of it too might have been some personal bias against like the analog side of things, because I'm trying to think about, I prefer the digital logic because that feels more familiar to me. And anytime like a resistor and a capacitor enters into the circuit, I'm like, I don't really get it. So, so some of this might have been like me personally sort of filtering out things that I should not have been filtering out. But in any case, something about this page here, kind of like drove me to say, okay, I should try this. Okay. Now I'm going to implement it now because I did try it off camera. And I didn't want to do that. This series was about learning on camera, but I was so frustrated that I ended up just doing stuff off camera. I'm going to kind of recreate it now and show you the problems I ran into. And I still don't fully understand everything that's going on here. And without an oscilloscope, I can't show you the signals, and And, I myself can't see them to debug things and get a better feel for it. So there's still stuff to learn, and it definitely doesn't hurt for me to just do it again. So I'm going to start here because this is where I started and things started improving when I found this circuit. Okay, so the first thing I'm going to do is just implement this as it's written here. It uses a relatively small capacitor, 0.1 microfarad, and I believe that's what this one is. Okay, I'm going to look up the capacitor code again just to make sure. This says 104 on it. Okay, yes, 0.1 microfarads, which matches what was used in this circuit. So I will use this one. I already have a 10K in my circuit that I will just reuse. And this is another thing too that I kind of wanted to point out. When I was first looking through this stuff, I wasn't really thinking about them clearly. I would see resistors and capacitors and be like, oh, geez, I don't want to get into that. I don't understand it. But, I completely failed to realize, of course, that my circuit already has a resistor in it, a pull-up resistor. And if you look carefully here, I mean, that's exactly what this is. It's just a pull-up resistor. It's like, wait a second, that's already here. Half of this circuit is adding a capacitor, and then this small resistor here, it's adding two components. And technically, I know from reading farther, and you could technically get away without this resistor at all, but there's a good reason that you should have it, and hopefully I'll remember to talk about that later. Now, I will hook it up and be right back. Okay, I believe I have this hooked up according to the schematic. I hooked up one thing slightly differently, which is I took out my jumper here that I had here going to ground on the chip or on the button, and the schematic showed it on this side of the button. I think for this purposes, I don't think it matters which side it's on, because as I remember, there's a law, I think, is it Kirchhoff's law, about the current through a serial connection is the same everywhere. So I would think that the purpose of this, as I understand it, is to limit, when you push the button down, it discharges this capacitor. That causes a bunch of current to go back through the switch, and that can be bad. Because even though it doesn't seem like there should be a lot during that momentary button push, if this wasn't here, you assume that the resistance is close to zero here when you push the switch. And if the capacitor was charged up to 5 volts, that means you have 5 volts going almost instantaneously to ground through the switch. I believe, according to Ohm's law, that's nearly 5 amps, right? It's not going to have perfect no resistance here. So that would be nearly 5 amps going through this switch. And as I found mentioned on another article, these little switches, they're not rated for much current. They're rated for like 50 milliamps maybe. So that's, way beyond what it's supposed to handle. Now, admittedly, it's for like nanoseconds or femtoseconds or whatever, because as this discharges, it gets, smaller and smaller voltage really quickly. But that's an interesting point. And I guess, on a certain time scale, that's probably way short, stuff is probably arcing inside here, So I guess that stuff like that can wear out the chips or the buttons. So anyway, that's why this is here. And I didn't realize that either. I can't remember if it's this article that talked about why that's there or another one, which I will hopefully mention later, and of course link in the description, that really, somehow explained it well, right? And I started to make sense to me. Anyway, long story short, that made it easy to hook this up because I can just replace this jumper with this resistor, and all I had to do was put this capacitor here. Now we'll just test it. And see, it's not working. This is exactly what happened when I first found this and hooked it up off camera. It didn't really seem to be working. In fact, it made everything worse. And I thought, okay, I'm doomed. I'm never going to find a solution. But then I kept scrolling, and we learned about this thing here called hysteresis. And the basic idea of this is that there should be a threshold where the voltage has to get above that threshold, and then it sort of locks on. And rather than turning off the moment you get below the line, it doesn't turn off again until you get below this second line here, this lower threshold. So that allows things to bounce around these thresholds and lock on or off. And you can see how that's being demoed here. The black line being the voltage bouncing all over the place, and this square wave being the thing that gets generated by virtue of, following this rule of having two thresholds. And it turns out that there's logic chips that have this in it, and that this thing is called a Schmidt trigger. And I actually have one. I have one right here, and in the TTL kit that I use all the time, an SN74LS14N is a Schmidt triggered hex inverter. Hex inverter just because, like, you know, there's 6 of them, but also that it inverts, which is kind of curious. So you put a signal in on one of the pins, and then the output is actually the inverse after it's been thresholded like this. Now, I couldn't find the actual datasheet for the HLF brand, which is what this chip is, but I found a Texas Instrument one, and you can see it's a hex Schmidt trigger inverters, and this datasheet is actually apparently for a whole bunch of chips. So it took me a little bit kind of guessing to figure out what all these symbols mean, but it looks like this VT plus is the upper edge. That's the upper trigger point for this chip, and I have this one, I believe. So at 5 volts VCC, it's around 1.6 volts. So your input signal has to get to at least 1.6 volts before it triggers as a positive signal. Then it has to drop to the minus, so the lower signal threshold at 5 volts is about 0.9. So it has to, or actually on the chip I have about 0.8. So it has to drop all the way to 0.8 before it switches from a high to a low on the output. So that allows for quite a lot of wiggle room. Okay, and the other important thing is the pinout. Now, the aspect ratio of this chip here doesn't really match the one I've got. It looks that ground is on pin 7, VCC is on 14, and then you just have one input here and one output right next to it. So I'm going to hook up the output of my switch. So instead of going to the clock input here, I'm going to take this into this chip. Then from the output of this chip, I'll go into the clock, and we'll see what happens. Boop. 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 Okay, so now I have it hooked up. The output of the switch after this initial debounce circuit, this resistor capacitor, goes over to the chip, and then from the chip over to here, and I'm kind of running out of space. So without moving everything around, I just put it over here. So we'll see what happens. I'll turn this on, and, you know, look at that. It works quite a bit better. Now, it still bounces a little bit. Since I don't have an oscilloscope, I can't check and see how long this is bouncing for, but I'm starting to suspect that this switch is maybe bouncier than I first anticipated, and the only reason it worked well before I put the debounce in there was because of the way it was hooked up. It only incremented when I lifted my finger, and you'll notice now, because it's an inverted signal, it now triggers on when on press, right? Because the moment this gets the signal over here, it gets inverted and sent to the counter, and now it goes from I think high to low when I push it, and I think this counts on the lower edge. And so ironically, that may have made the bounce worse, because my theory is that the bouncing is worse when I first press it down and not so bad when I release it because of how this switch is constructed. I might be wrong about that, but I think that might be what's going on. So then it occurred to me, well, you know, how is this resistor capacitor chosen? Well, it turns out with RC circuits, you can simply multiply the capacitance by the resistance, and it gives you a time in seconds. And that time in seconds, I think it's roughly 60%. It means the capacitor is roughly 60% full in that amount of time. Well, that coincides pretty nicely with the voltage level required for a true on this chip. But that means you can adjust the time simply by putting a bigger capacitor in here. Boop, boop. It works so much better. I mean, it doesn't really feel like it bounces at all. Now, because this is and I forgot it already, 10 microfarad capacitor, and this is a 10K resistor, you can calculate how long the time element is, and that's easy to do with Wolfram Alpha because you can just put in the units and let it figure it out. Here's Wolfram Alpha calculating 10 microfarads times 10 kiloohm, and as you can see, that's about 100 milliseconds. Okay, so it takes roughly 100 milliseconds for the capacitor to fill up to, I think it's, 60% or something like that. So that means that when I leave it sit here, because of the way this is hooked up, when I first turn it on, the capacitor immediately starts to fill up. and it takes it about 100 milliseconds to get high enough to trigger the Schmidt trigger, which in turn causes it to invert the signal here. And when I push the button, I'm actually shorting this capacitor to ground, because you can see where it's hooked up, right? If I push the button, this leg of the capacitor connects directly to ground, which is where it is here. So they become shorted together, and that drains the capacitor pretty quickly. And because this is a 1K, it drains it even faster. So you can see it drains in about 10 milliseconds because of the way the current goes. So this is all, you know, pretty great. I mean, honestly, it works really well now. I'm not sure what to do to make it much better, to be honest. I mean, aside from, you know, tidying up the wires and reordering everything on here, but I don't think I'm going to bother with that because, you know, it works, and I think I kind of understand it. But the next thing that I want to talk about now, so now bounce, I think, is dealt with. The other thing that, and you may have seen it once or twice in the video already, is when I turn this on, it still sometimes starts at some totally random number. And I have, you know, if I care, I have to manually reset it. That's been bugging me, and I figure there's got to be a solution to this. But here's the fun part, I think, or at least I think it's fun from a learning point of view. Doing this debounce circuit and starting to kind of understand how these things, you know, fill up and how that changes the voltage on the one side of the capacitor, you know, and like why you tap it from the middle like that, got me thinking, I bet that's how you make something like a startup circuit. Like when you first turn it on, the capacitor is going to fill up, and that takes it a moment, right? And during that moment while it's filling up, what if we could hold the reset pin low so that it's permanently in a state of reset until the capacitor gets full, at which point the voltage ends up being high, right? And it'll stop resetting. That should mean that if I just hook up another circuit like this one, you know, basically just another debounce circuit, honestly, on the reset pin, I think that I can solve my reset problem where it should always start reset instead of just, you know, at random garbage values. So I'm pretty sure that the way to hook that up is I need to have a high signal after the capacitor has charged up and a low signal initially. So I think that means that I hook it up almost identically to how I have this here, because right now when I turn on the circuit, and the button's not pressed, current should be going through this resistor into the capacitor and charging it. That means that initially this side of the resistor is positive and this side is negative essentially and increasing as the capacitor fills, which is pretty much exactly what we want, I think. Because we want it to be positive at the end when it's done filling so that the counter works. But we want it to seem negative, to read as negative right at the beginning. So since this takes about, with a 10K, takes about 100 milliseconds, I think I can just use another 10K and another one of these capacitors and hook it up right here to the reset pin, and that may just do it. Okay, I hooked up a resistor and capacitor. It's just a mirror image of what I did for the debounce circuit hooked up to here. And essentially, and I removed my reset jumper. So essentially this is, you know, pulling the reset pin to high constantly. It's just that because of the way these resistor capacitor circuits work, as the capacitor charges up when I first turn it on, that causes this voltage here to be low initially and then build and build and build as this gets full. When it gets totally full, then current essentially is going to stop running through here, but this is being held high then, which is exactly what we want. We don't want it to be in reset. We want it to read as reset initially when we first turn on, and I think that's what this does. So when I turn it on now, it starts at 0, and of course, it's hard to know with absolute certainty. Possibly if I had an oscilloscope, I could hook up probes here and maybe measure it right when I turn it on and see what happens to the voltage levels. I've tried turning this on and off a lot of times, and as far as I can tell, it's always 0 and it's always working. I don't know if that's totally reliable. It seems a little bit strange because I think between power cycles here, this capacitor would presumably be storing some amount of electricity. I don't think it would be draining immediately, but something must be draining it. I suppose maybe a resistor could be installed across that to ensure that it drains, like maybe some high resistance value. I don't know. It doesn't. Oh, I was just about to say I've never seen it fail, and there it failed. If I put a resistor across this, it'd be straight to ground, I think. Wouldn't it always be discharging a little bit? I suppose it might, and this one would be always topping it off. So you'd probably want kind of a large one to keep too much current from flowing, but not a really huge one because you don't want to take a long time to discharge. So maybe I'll throw 100K in there. Okay, I have a tall 100K in here. It's getting very crowded here, and I imagine this is going to be very hard to see on camera. I'll try to zoom in, but I only have so much resolution to work with here, so we'll see how it goes. Since this is a 10 microfarad and this is a 100K, it'd take about a second or so to discharge, and that's maybe a pretty long time, so maybe 100K is too much. Oh, look at that. I managed to get it to fail on camera. Excellent. Well, how about I'll just put a 10K in there and see what happens. Okay, I swapped out the 100K for a 10K, and it's connected, again, very difficult to see, but it's basically just connected across the legs of this capacitor. So it should mean that, you know, when the power's off, it's going to drain through here and I guess just get dissipated as heat. So since this is 10K now, it should be about 100 milliseconds to discharge it 60%, I think, is how that works. So it should probably get it below the threshold. And I don't know if I could turn this on and off that quickly anyway because of the physical switch here. So let's see. Okay, that's looking pretty good. And the counter still works because once the capacitor is fully charged, that pulls the pin high, which disables the reset and allows everything else to work. So hey, I'm pretty happy with this. I'm a little frustrated with how difficult it was to get here, considering several false starts in the video and lots of bumpy roads and whatnot. But I am pretty happy with it because I think I have a stronger understanding of not only, you know, the RC circuits, but like how and when to use them. And it's kind of cool because I was kind of unconsciously or maybe consciously avoiding this kind of stuff, and the debounce really forced the issue, and I'm kind of glad I didn't just skip it. You know, I feel like if I was building this stuff for an Arduino or something, I would absolutely have just imported some debounce library, you know, and written some code, because as far as I can tell, that sounds like that's a pretty common solution if you're dealing with an Arduino. Just hook up the switch, import some debounce library or, you know, something like that, and just don't think about it. But I'm actually really glad that I did it this way because this is what's actually going on, and it's really nice to see that. Now, another article that I came across was one of the articles in this series here, The Ultimate Guide to Switch Debounce by Max Maxfield. I'll put links in the description to a search result on their site that gets you all the parts. The parts aren't well connected together. I guess I could also link to part 9, which I think links them all backwards, but they don't really connect forward as far as I can tell, so that part's a little annoying. But I read this whole entire 9-part series, and honestly, it was really good. I mean, I feel like it was pretty well written and, you know, a little bit fluffy and a bit of repetition from time to time. But in general, this 9-part series, I think, is the thing that really helped me the most start to kind of feel like I'm understanding what's going on here. It's also the article, maybe not part 1, but one of the parts in this series is also the thing that really pointed out that issue of needing this other resistor here, because when you discharge your switch, that current has to go somewhere, you know, and like how much current that is. And it's way more than you would think, but that's because it's just such a short time period and there's no resistance there, or nearly no resistance. In some ways, I'm glad this video was a pain in the butt because it led to a few more searches. You know, like I thought I'd done a whole bunch of searching on the debounce thing, but I don't know how I completely missed stuff. I'm pretty happy with this. I still want to get to using a 555 timer, probably with this same basic circuitry here. the irony of that is that I might not need any of this debounce stuff. I could just put a timer in there and get it to generate pulses. But one of the things that I didn't like when in my skimming of 555 timer circuitry was, they have a lot of resistors and capacitors, or maybe not a lot of, but a handful of them. And, honestly, I kept shying away from that. So now I think I have a really good understanding of why they're there, or at least a better understanding. I'm by no means an expert. Don't even get the impression I'm an expert at all with any of this stuff. But I have a much better understanding of why that's there now and how that is used, I believe, to set the duration of the timer. See, now, and that's starting to make a lot of sense. It's like, how could it do that? Oh, it's because, it fills up with this and the voltage levels change. And anyway, suddenly that stuff makes a lot of sense, but that's for a future video. Well, I think that's all for this time. I've been very blown away by the number of views that my videos have been getting, and I'm very grateful for that. I know there's been a lot of comments too, and I don't always reply to all of them, largely because I'm not sure what to say. A lot of you clearly know far more about this than I do. So, again, I am no expert at this, and that is in fact the point of these videos, is that I'm just sort of learning it. I knew some stuff by osmosis, but not in depth. And I still probably am not going to learn stuff deeply in depth, but what I really wanted was what I got out of this process here, I think. I really wanted to have this happen where I struggle and have some problems and then come away with it feeling like, this thing that used to be scary is not so scary now. And I'm kind of, a little bit looking forward to more of those kinds of things in the field of electronics and circuitry. So I'm going to keep trying to make them as long as we have ideas to do for them. So we'll see how that goes. Anyway, if you like them, subscribe if you haven't, thumbs up. And if you don't, then do the opposite of those things, I guess. And I will see you next time. Bye. It still feels very silly talking to the videos. Very silly.